Okay, hello everyone. This is Ken from Castool. Welcome to my second webinar talking about toolings for extrusion and die cast. However, today I will focus on steels, heat treat, and nitrides only. And the areas or the steels I'm gonna focus on will be primarily on shot sleeves and for aluminum die cast. We can see shot sleeves in aluminum die casting is subjected to high temperature, high thermal fatigue, severe wear, erosion from aluminum, and corrosion from aluminum. So on the left, you can see a schematic drawing of a shot sleeve in a machine and also with pistons or plungers from left to right, from parking to injection positions. On the right, you can see when you open the die and you shoot a thermal camera on the sleeves and the machine, the temperature distribution of the sleeves and also the machine as well. You can see the temperature is pretty uneven. It can go as high as 300 degrees Celsius, which is when the die is open. So when the aluminum is actually touching the sleeve, the temperature can shoot up even higher than 300 degrees Celsius. So that limits our choices for the steels to work with for the shot sleeves. The most common one people use is H13, and H actually stands for hot work tool steels. And for the H category of steels, you do have three different based materials. You have a chromium based from H10 to H19, tungsten based H20 to H39, and molybdenum based 40 to 59. Because of a different base alloy, they have a different characteristics. For chromium based, you can air harden it, which is making it more economical. And because chromium is more corrosion resistant to water, you put a lot of chromium in stainless steel, make it stainless. So you can use the steel with water cooling while in services. For tungsten and molybdenum, that's gonna become a problem because tungsten and molybdenum usually are hydrophilic. They like to grab hydrogen from the water, and then they are prone to cracking. So that's another benefit for using H13 as well. So now you got your steels. When you actually get your steels, it's before heat treated, or there is no heat treat process done to it. It's just coming out from the mill. So you can see here from the NACA guideline or recommended austenizing, quenching, and tempering for the heat treat cycles, it has 4 different temperature peaks. The first one, the purpose of first one is try to melt, or not melt, or solutionize all the alloys in the steels. You can see the chromium base will be chromium or molybdenum or tungsten back into the steel, and now you have first temper, second temper, and the last stress temper to release the alloy back out to get the property that you want. However, this is a guideline developed using small chunk of steels. So when you heat treat a sleeve, which is 40-inch long and perhaps 20-inch in diameter, the property will be different, or the story is going to be different. The process is going to be different because the steel shot sleeve responds to heat or temperature differently. You can see on the chart to your left, there's a size effect on heat treat. So the larger the size you go, you have to increase the higher temperature or hold it there longer. But the problem is when you hold it there longer, you're going to anneal the steels also. So you got to make sure your shot sleeve supplier has the good knowledge and experience in building different sizes of sleeves, because obviously small sleeves will be different than large sleeves, which is very important. And now we look at the specs of H13, the most commonly used steels. On the top row, you can see which is a premium grade H13, and it always tells you, because we know from steel mills that the way they control the process, so we have a window for specs. But you can see the most important alloys in the H13, which is chromium, molybdenum, and vanadium, the last three columns, they do give it kind of a leeway there. They are saying for chromium 5% and 5.5, it's also within spec, and for molybdenum and vanadium as well. So you can have a two H13s with two different alloy percentages or concentrations. That would create a problem because even if, let's say, hypothetically everything is identical, they have a same furnace, same way the heat treat, quenching, tempering it, because of an alloy concentration in these two steels are different, the final property of the H13s will be different. You can see on the left, you see when you increase chromium concentration, the Rockwell or hardness of the steel will increases. And also on the right, molybdenum, it also shows you that when you increase the molybdenum concentration, the Rockwell or the hardness of steel also increases. So then we would expect H13A has low chromium, molybdenum, and vanadium on the spec of that steel fall into the specs will have a lower property compared to H13B, which is understandable. So what does these two different harnesses mean to the end user? On this chart, you can see if we put this H13 material and subject it to three different temperature cycles, 600, 650, 700 degrees Celsius. At the bottom of it, it shows you the thermal cycle or temperature cycle it goes through. And on the left, it shows you the total crack length, means that if you see there's a little crack, let's try to find out how the circumferences of the crack, or try to add up all the crack lengths together. So that's the total crack length. And I actually converted the tensile into Rockwell, so it's easier for most of us to see. You have 40, 46, 52 Rockwells, and they all respond to, or they all have a different heat checking responses or resistances. And on top of that, when the Rockwell is different, the hardness is different, the impact will be different as well. So for the heat checking, it's positive in proportion. When you have a higher Rockwell, the heat check resistance is higher. But for the toughness, when you have a higher Rockwell, the toughness is lower. And I put this two into a graph and also put into where the resistance index into it. And you can see for the heat checks, they are not, first of all, it's negative, it's positive in proportion. I mean, the shorter the total crack length, the better the heat check resistance. But they are not linear. You can see it starts to go from 30 to maybe 40, kind of linear, but all of a sudden it becomes better from 40 to 50. And for the toughness, it drops quickly from 30 to 40 as well, from 45 to 50, more kind of plateau out. So for most of a short sleeve application, H13, the window from 44 to maybe 50 or 52 Rockwell is a good window to start with. And then you can start to tweak around. Let's say if you want a higher wear resistance, you can increase the Rockwell. Excuse me. And in the second graph, you see, let's say we start with 44 Rockwell compared to the other H13 for 48 Rockwell at cold, which is the room temperature, and then you put these two steels at the two different temperatures from 100, 200 through up to almost 650. We can see the trend of the Rockwell drops, how they drop. And what's interesting is if you start with 4 Rockwell differences, they will end up with 4 Rockwell differences up to 585, roughly 585 degrees Celsius. So what does that mean to us or the die caster? So as long as the temperature is lower than 585 degrees Celsius, what you put in, you should expect you will get from it. Let's say if you put in 44 Rockwell to start, it should last up to 585, still have 44 Rockwell and doing the job for you. And from 44 Rockwell to 48 Rockwell, we can see the heat check-in reduced by 50% from 6 millimeter to 3 millimeter, but the toughness reduced a little bit less, which from 20 to 17, and wear resistance increased even less, is at from 8% only. So what if that we need the steels to withstand or hold up to higher than 585? What we can do is we can nitride the steel, or we can modify different steel composition in the steel. As we know, when you increase molybdenum or chromium, the hardness of Rockwell is going to increase as well. So in Castor, we modify or we tweak the composition in H13. We increase the molybdenum from 1.3 to 4% because molybdenum gives a better strength or hardness. So the end result is we can see the tempering curve. The tempering curve usually means when you try to temper or when you try to soften the steel. The red one is the H13. The blue one is the newly modified thermal steel, which is belongs to Castor proprietary steel. You can see from 400 degrees Celsius to 650, it's all around 2 to 3 Rockwell higher. So using that 2 to 3 Rockwell higher and also the heat checking and toughness and wear resistance index, we can have a pretty good idea. Compare two steels with the other conditions identical, what can you get from the steel? Just to kind of have a more quantitative result, we actually put these two steels to the lab and do the testing. And we can see here are the percentage that actually shows you at 430 degrees Celsius how much stronger the H13 or how much stronger the thermal steel is compared to H13. And the molybdenum added into the steel also have some added benefit because the molybdenum itself is a refractory element, so it has a very high corrosion resistance to aluminum. When we increase from 1.3% to 4%, we would expect increase in corrosion resistance of the base material because you can see the nitride H13 for every hour it will lose 37 milligram, but for molybdenum every hour it only loses 2 milligram, which is about 15% higher. Also, when you put molybdenum into the steel, the soldering resistance of steel should also increase as well because, again, molybdenum, titanium, and tungsten are refractory-based material, and then they don't like to, combine with the aluminum, so the soldering resistance will increase as well. So you have a choice to, when you are die casting aluminum with very high pour temperature, let's say maybe 700 degrees Celsius, 710 degrees Celsius, because your process requirements, or you're die casting some structural alloys, or you do see some erosion issue, especially under your pole area, we would suggest you use thermal-based sleeves, and on different sizes, we will have a different design for the sleeves as well. And on the larger ones, you can have an insert only because insert is particularly, that's the area that sees the most temperature fluctuation and most erosion section as well. And even better, that you can bore weld or you can upgrade your sleeves, meaning that you can have a base sleeve which is made of H13, which is used, worn out, we will board it out, board it open, and then we will weld a new layer on top. Since it's a welding, so you do have a choice to weld H13 or thermal steels. And another benefit of welded a layer on top is because when you weld it, the steel goes to melting and quenching in milliseconds. So that very high quenching rate will have a very high Rockwell. And what end up with it's a bulk is 4648 Rockwell, and on the surface it's 5052 Rockwell. So what you are getting, you're getting the good parts of two different alloys, because you can have a toughness of 4648, but on the surface you will have a heat checking resistance and wear resistance of 5052 Rockwell because it's a welded one. And now you have a different choice of material to use. So now we covered a little bit on the steel from the specs and a little bit on how we heat treat the steels. And I'm going to talk about nitride, which is actually a very interesting topic because people do nitride a lot, and there's a very big, vague definition of nitride K-steps. So the definition of K-steps is you go from surface to the bulk of material up to 50 Rockwell. So when you say I want 8,000 for the nitride, that means they will nitride the steel when the Rockwell is gonna drop to 50 Rockwell and at the 8,000 dip. And if it's 10,000, it will be 10,000 deep. But what about the profile of the harness? On this schematic drawing, you can see the surface Rockwell is 70, and the K-steps is 50 Rockwell, but you do have A, B, and C, three different profiles. First of all, when you do a harness test on the surface, you will get 70. And when you ask for the certs, you will get 10,000. But A, B, and C is going to perform differently because the saturation or the integrity of the nitride is different. A is better than B and it's better than C. And on top of that, this is when you want to check the quality of the nitride. It's a destructive method. That means you have to cut open your sleeves, and rarely people will do that. They will just trust their nitrider. And I'll quickly cover three different nitride techniques. You have an ion nitride, plasma nitride, salt bath, and gas nitride. You can see their processing temperature are a little bit different. Ion can be the lowest because you have a plasma which provides extra energy on top of the temperature, so the temperature of the sleeve can be lower. And the salt bath, because it's put into a salt which has a better heat transfer, so the temperature of the sleeve itself can be lower again as well. But the Rockwell they're able to achieve is almost identical. So a lot of people will say, they are almost identical. I think they will work the same. But if you look a little bit deeper on salt bath, gas, and plasma or ion nitride, you can see on this micrographs, on your left, it's a salt bath. And I highlighted the white layer or the compound layer, which gives you the corrosion and erosion and the wear resistance. And the K-steps actually gives you the fatigue. You gotta be a little bit careful about what are you asking for nitride to do. So the salt bath creates a very compact white layer. So it's very good for dry sliding wear because it's pretty compact. And for the gas and the plasma nitride, due to their nature, it's involved with the gas. So if the process is not controlled or you don't control it properly, you can create some pores or porosity on the white layer. There are some debates. People say it's good for lubricants because you will have a loop going to the little pore and it creates better lubricity. So it's kind of depends on application. And The plasma, because you can change the gas and also lower the temperature, the pores in the white layer generally is smaller compared with gas nitride, but the salt bath can create a very compact white layer. So that means salt baths should have a smoother surface, and gas and the plasma should be a little bit rougher. So you can see initially the steel before heat treat or before nitride, the surface is 32232 micron RA, which is very smooth. And when you subject this steel to gas nitride, the roughness increases depending on temperature. The plasma is also gonna roughen the surface as well, but it's less than the gas because plasma creates less porosity in it. So just due to the nature of process, the nitride case uniformity means, let's say I want 10 thou, and I'll always get 10 thou bang gun across all dimensions. Salt bath is the better one because the salt bath, when you put it into the bath, the temperature of the sleeve is very uniform, and nitride is a temperature activated process. You have a uniform temperature, so the case is depth is very uniform. And now you have a salt bath is better than ion and better than gas. It's just because for the gas you need to operate at a higher temperature. There's a higher danger to have temperature distribution problems, and the gas usually generally is a less preferred conductor for temperature, for the heat. And distortions is on temperature distortions. When you put the steel back at high temperature, there's a danger to distort the steel. Since gas would have to use the highest temperature or nitride in temperature, the distortion in gas potentially will be the highest. The second one is the salt bath, and the lowest one will be the ion, because ion you can have a low temperature of the steel and use plasma to activate the nitriding process. But what's more interesting is when you put these three under wear test. On your left, it shows you you have a wear rate, and for different nitriding technique under different load. But I summarized the table for you, which is make it easier to see. Let's say if I pick two loads from 10 Newton and 100 Newton. If you have a 10 Newton load, ion performs the best. So it will only lose about 2 times 10 to the negative 4 compared to 8 and the 3. But what's interesting is when you increase the load, the champion is different. Now when you increase the load, because salt bath has more compact white layer, it's able to resist the wear better than the other two. What that means is, to your sleeves, there might be a difference when you use ring type of plunger tip or solid type of plunger tips. Because solid type of plunger tip, inherently you're gonna have a more force from the tip to the sleeves, and so you should see, according to this wear resistance indexes, the salt bath nitride and the gas nitride should perform a bit different because you use different tip types. And obviously, when you increase the load from 10 to 100, all three of the nitride techniques, the wear is gonna go faster. So now we talk about wear of the nitride, but nitride generally increases the wear, but nitride itself is not a good corrosion layer against molten aluminum. So what we can do, or what Castle is doing right now, is after you nitride, we put a protective layer on top. So its protective layer is very thin. It's less than 1/10 of thou, so which will not change the dimension at all. And it's on top of nitride. Uh, the I would say the advantage or the difference of this 3P process compared to conventional coating process is conventional coating process is physical vapor deposition. It will suffer line of sight limitation. That means it's very easy to coat coat OD, outer diameter, but it's very problematic to coat ID, inner diameter. But for the sleeves, ID, inner diameter is the most important part that we want to protect with molten aluminum. For the 3P process, there's no problem to form the 3P layer on the OD or ID. Also, this one shows a little bit about friction coefficient comparison between steels, nitride steels, and nitride steel plus 3P on top. You can see friction coefficient is going to reduce further from nitride steels, and working temperature, that means at what temperature that added 3P layer is going to decompose is 850 degrees Celsius, which is higher than most of die-cast would ever dream of on their pro temp. So this will bring us to my last slide, just focusing on the 3P. It's a very minimal addition on top of your dimensions. As 9 times better improvement over conventional nitride corrosion resistance, 25% less friction coefficient, and higher working temperature than your die-cast conditions. So if you have any questions, you're welcome to email me by sales@castool.com or ken.chien@castool.com. Thank you for your time. Have a good day. Bye-bye.